Okay guys, in this video we are going to discuss phase diagrams and related topics. Um, and so just a few definitions from general chemistry. Recall that the term phase refers to a form of matter that has uniform composition and a definite physical state, which could be solid, liquid, or gas. So we would say that these would be a single phase. Related terms to this, the term allotrope refers to a particular form of an element. So if you're talking about oxygen, you might be referring to diatomic oxygen or possibly ozone, O3. Those are different allotropes of oxygen. And then different solid states of the same substance are called polymorphs. So for example, there's multiple types of, let's say ice, for example. The ice that we're used to is called ice 1, but there's a whole array of ice that is possible under abnormal conditions of high pressure. We'll look at a phase diagram of water that shows us the different polymorphs of water. Related to this, although this chapter is focused mostly on pure compounds, you can also have mixtures, and so there's homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are things like solutions where the different constituents are mixed together at the molecular scale so that they're completely evenly distributed throughout one another. You can also have solid phase solutions like metal alloys. Those are also homogeneous mixtures, and these are a single phase. Contrast that with a heterogeneous mixture where you have multiple components present and they are in different phases. That is, you can distinguish between the two phases. And so here's just a cartoon diagram illustrating the difference between a homogeneous solution and a heterogeneous solution, where you can visually detect, even though it may be difficult, you can actually distinguish one phase from another. For a solution, all of the molecules are uniformly mixed around, and so you can't distinguish one part or not from another at the macroscopic level. So here, just a qualitative question: how many phases do we have for the following systems? A solution of sodium chloride would have one phase. It's all in the aqueous phase. A block of ice would also have one phase, and even if you chopped it up into multiple chunks of ice, it would all still be the same phase. So parts B and C also have only one phase. However, a slurry of water and ice, so think of slush, even though it may be difficult to distinguish between the ice and the water, it's still two phases. And for the reaction in part C, we would have three phases. We would have a calcium carbonate phase separated from a calcium oxide phase, and then there would be a carbon dioxide phase as well. We'll be talking about phase transitions in this chapter, and so this is where we have the conversion of one phase to another. There are a set of generally endothermic phase transitions, so fusion, which is a synonym for melting, going from a solid to a liquid. That's an endothermic process. Vaporization and sublimation are also endothermic. Notice in all of these endothermic examples, you're going from a more condensed phase to a less condensed phase. For the reverse of those, of course, would then be exothermic, so freezing, condensation of a gas to a liquid, and deposition of a gas to a solid. These are all exothermic phase transitions. Phase transitions occur spontaneously, and they occur at a constant transition temperature for a given pressure. So let's take a look at a cooling curve here. So at high temperatures, we initially have, notice we're plotting this as versus time, At high temperatures, we've got our liquid. If we just let it sit there in equilibrium with the surroundings at a lower temperature, the liquid is going to cool down somewhat rapidly until it gets to the freezing point. At the freezing point, you're going to note this plateau here where for some time the temperature of the liquid-solid mixture, equilibrium mixture, will not change. And so here you've got liquid and solid in equilibrium with one another. The liquid is being converted into the solid. Once all of the liquid is converted over, then we're going to have cooling of the solid, and it's going to cool at a different rate than the liquid did in general. This slide introduces us to the term chemical potential, which is something that we're going to be working with over the next 3 chapters. Chemical potential is very important for understanding equilibrium problems. And in this chapter, we're studying phase equilibria. For a single component system, the chemical potential, which is represented by the symbol mu, is simply the molar Gibbs energy. Okay? Gibbs energy is so important in chemistry that the molar Gibbs energy gets its own symbol and its own name, the chemical potential. So it's really nothing more than the Gibbs energy of the system divided by the number of moles of compound within that system. Okay, so when you think chemical potential, just think, for now, just think about molar Gibbs energy, the same thing. So here's the rule for phase transitions. Okay? At equilibrium, the chemical potential of a substance is constant throughout every phase of that equilibrium. So let's suppose that we've got some alpha phase in equilibrium with its beta phase. Everywhere within the alpha phase, the chemical potential has the same value, and it's equal to the chemical potential of the beta phase, all throughout the beta phase. And so here's a diagram. I don't know, let's suppose this is a solid and this is a liquid, or it could be flipped around. This could be the solid and this could be the liquid. It just depends on the substance. All throughout this equilibrium system, the chemical potential of that substance is the same. Okay? And so that's the definition that we're going to be using for equilibrium. And it comes from thermodynamics, and so that's illustrated here in this slide, where we discuss the spontaneity of a process. So let's consider 2 states. Okay, so we have state 1 here and state 2. So these could be 2 phases. Perfectly fine. I think that's what we should focus on now. So phase 1 and phase 2. And what we're going to do is we're going to transfer an infinitesimal number of moles from phase 1 to phase 2. So think of this, we're converting one phase to another. And so we're going to ask ourselves, okay, what's the change in the Gibbs energy for doing that? So you can write it out like this. So the total change in Gibbs energy is going to be the change in Gibbs energy for this phase plus whatever the change in Gibbs energy is for this second phase. Okay, so you've got two things. Something's transferred. So both the Gibbs energy of both these subsystems changes, and we're just adding them together. These are extensive quantities right here. Chemical potential is an intensive quantity, and so the way we can work it out is we can write, okay, we've got some chemical potential. This is the molar Gibbs energy for this phase 1. And then, the number of moles of phase 1 is going to change by some amount dN1. And the chemical potential for phase 2 is mu2. And then, the number of moles of phase 2 is going to change as well. Okay, now, these 2 changes are related to one another, right? So if we're transferring dN moles, then the change in the number of moles of phase 1 is going to be negative. So we can write this as mu1 negative dN plus mu2. And the change in the number of moles in phase 2 is going to be plus dN. Now that we've got the 2 terms on equal footing, we can rewrite this as mu2 minus mu1 times dN. Now this is a positive quantity, right? This represents a fixed amount of moles, and so this isn't negative. But we've got this sign difference between the two chemical potentials here. Well, what's our criterion for spontaneity, of course? dG will be less than 0 for an isothermal, isochoric, or isobaric process. And so when will this be negative? It'll be negative when the chemical potential of phase 1 is larger than the chemical potential of phase 2. Okay, so if that's the case, if the chemical potential of phase 1 here is larger than the chemical potential of phase 2, then dG is going to be less than 0, and that's going to indicate that this forward direction is spontaneous. Well, it could be that, that's not true, right? So what would happen if the chemical potential of phase 2 was larger than the chemical potential of phase 1? Well, then you're going to get a positive dG, which means that, in fact, the opposite direction would be spontaneous. The third possibility, of course, is that the two chemical potentials are the same. Okay, and so if mu1 equals mu2, then dG equals 0. That corresponds to a reversible process, and we would have an equilibrium between the two phases. And so that's why this is the evidence for why I'm saying here on this slide that this is the criterion for phase equilibrium. The chemical potential of that component in all phases is the same. That's the definition of equilibrium. And it's nothing more than the second law of thermodynamics. It's just been kind of buried in all of this notation that we're introducing. So here we're going to think about ice in the context of molar Gibbs energy and chemical potential. So we all know that ice is the stable form of water at temperatures below 0 degrees Celsius, but above 0 degrees Celsius, liquid water is more stable. So just comment on the difference in the molar Gibbs energies for the two phases, both below and above 0 degrees Celsius. Well, the rule is that nature goes from high chemical potential to low chemical potential. So whichever phase is most stable under a given set of conditions, that would be the phase with the lower chemical potential. So below 0 degrees Celsius, ice will have a lower chemical potential than liquid water. Above 0 degrees Celsius, the liquid water would have the lower chemical potential than the solid water. So chemical potential, just like Gibbs energy, depends upon conditions of temperature and conditions of pressure. And so you can change the chemical potential of the different phases by simply changing the temperature. And above the melting point, the liquid has the lower chemical potential. Below the melting point, the solid has the lower chemical potential. Here we have just a little calculation. There's nothing to this really. So this is calculating the molar Gibbs energy of vaporization for water at 298 Kelvin. So we would do liquid water in equilibrium with water vapor. The enthalpy of vaporization at 298 Kelvin would be the enthalpy of formation of the water vapor minus the enthalpy of formation of the liquid water. And so we would plug in here minus 237 minus negative 299 and we get 62. That would be kilojoules per mole. When you go from a more condensed phase to a less condensed phase, it's typically, almost always, endothermic. All right. So we will come back to the topic of chemical potential. For now, we are going to talk about phase diagrams, Phase diagrams are a useful tool for understanding how a phase equilibrium can be affected by changes in temperature and pressure, and also concentration, although we're dealing with pure substances mostly in this chapter. Okay, so let's just look at one here. You've seen this before probably in general chemistry. We've got, in this graph, we're plotting pressure values versus temperature values. And the different regions that you see here indicate which phase is most stable under those conditions. So at low temperatures and high pressures, the solid phase is favored. At moderate temperatures and moderate pressures, the liquid phase is favorable. At very low pressures, the gas, the vapor phase, is favored. Okay, so these are the different regions that you see here. This is a generic phase diagram. This is something that you want to keep in mind. Keep this diagram in mind when you're thinking about phase diagrams. It would be useful if you could sketch this diagram, from memory. The curves that you see here, these different lines that you see, these are called coexistence curves, and they represent the values of temperature and pressure at which the two phases that are meeting are in equilibrium with one another. So this curve here, this would be the solid-vapor coexistence curve. This one here, this is the liquid-vapor coexistence curve. And this one is the solid-liquid coexistence curve. Everywhere along this curve, you'll have solid and liquid in equilibrium with each other. Vapor pressure. So here I have a little diagram. This is showing you we've got a sealed container that's got some liquid or solid in the bottom, and then that liquid or solid comes into equilibrium with the vapor phase above. Okay, so an equilibrium is established. The pressure of that substance in the vapor phase, when it's in equilibrium with either the liquid or the solid, is called the vapor pressure of the liquid or the vapor pressure of the solid. Those are indicated by these coexistence curves. So this curve here can also be called the vapor pressure curve. It's the vapor pressure of the liquid. It's the vapor pressure of the vapor that is in equilibrium with the liquid. You'll see that it's temperature dependent. As you increase the temperature, the vapor pressure of the liquid increases. This would be the vapor pressure of the solid in equilibrium with its vapor. So the normal versus standard boiling and freezing points. Let's imagine that 1 atmosphere is right here. And let's draw a horizontal line across the diagram, okay, where that horizontal line encounters the liquid-vapor equilibrium curve. This is called the normal boiling point. That is, we have 1 atmosphere pressure here. When the vapor pressure of the liquid equals 1 atmosphere, that corresponds to the boiling point of the liquid. So that would be the boiling temperature. Likewise, when the 1 atmosphere horizontal line crosses the solid-liquid coexistence curve, that would indicate what the normal melting point is of that liquid. The so-called standard boiling point and the standard freezing point, that would be for a pressure equal to 1 bar. And so the normal boiling point and the standard boiling point are pretty close together. They're not quite the same. They're just at slightly different pressures. Lastly, we've got the triple point and the critical point. The triple point is a special point on the diagram where the solid, liquid, and vapor regions meet. So all 3 coexistence curves converge to the same point. And so at this special point, the triple point, you've got all 3 phases coexisting with one another in equilibrium. Each substance has its own unique triple point. The triple point involving liquids is unique. And then there are different, as we'll see in some of the example diagrams, substances have multiple solid states, and so there can be other types of triple points involving 2 solid phases and a liquid phase, or even 3 solid phases. The critical point, we've already talked about this in the context of gases, and it's the same thing from that chapter. The critical point is a point on the phase diagram that marks the end of the liquid-vapor coexistence curve. Beyond that point, there's no distinction between the liquid and vapor phase. We have what's called the supercritical fluid. And so all the properties of liquids and vapors, they all converge at that special point. For example, the density of liquid and the density of a gas, as you approach the critical point, they converge to the same value. The same thing is true for for example, the enthalpy of vaporization, which is temperature dependent. As you approach the critical point, the enthalpy of vaporization goes to 0, such that there's no difference between liquid and vapor phases. We just have the supercritical fluid. Note that there is no such ending for the solid-liquid coexistence curve. So there's no critical point along the solid-liquid curve. You'll see some other diagrams that I'll show in a few moments. Here's an example of observing supercritical behavior. So you've got, let's call this the liquid and this is the vapor phase. As you approach the critical point, you'll notice that the 2 phases start looking more and more the same, and the meniscus between the 2 phases will eventually disappear once you go past the critical point. There's no problem to solve here. This is really just more of a factoid. The triple point of water is at 273.16 Kelvin and 611 pascals. All 3 phases of water coexist with each other at equilibrium. And in fact, this special point was, and maybe still is, used as the basis of the Kelvin temperature scale. Let's talk about another aspect of the phase diagram. This is going to be called the Gibbs phase rule. It specifies the number of intensive variables that maintain P phases and C components in equilibrium. Okay, so if you've got a set of C components, right, C is the number of components that you have in equilibrium, distributed among P phases, then you can modify F intensive variables in order to maintain everything in equilibrium. And what do I mean by variables? I'm talking about things like the temperature, the pressure, and concentration. Okay, so these are variables that you can alter. And so the Gibbs phase rule tells you how many variables you can alter and still keep everything in equilibrium. We make a little distinction here between the term constituent and the term component. So a constituent is any chemical species that is present in your sample, and then the term component refers to constituents that are chemically independent of one another. And you'll see what I mean in the next example. So a solution of ethanol and water has 2 constituents and 2 components, an ethanol component and a water component. A salt solution has 3 constituents, water, the solvent, sodium ions, and chloride ions. However, there's only 2 components because sodium ions are not independent of chloride ions in this example. For example, you can't change the concentration of sodium ion without changing the concentration of chloride ion because they're related to one another through charge neutrality. Okay, so there's only 2 components, but there are 3 constituents. So what we're going to set about doing here is calculating the number of intensive degrees of freedom that we can freely change without disrupting the equilibrium amongst the phases. So we'll start with a single component system. So the value of C is equal to 1 in this case. And then we'll just suppose, okay, if we have only one phase in equilibrium, then we can vary both temperature and pressure independently of one another. So the value of F is equal to 2 in that case. And this corresponds to an area of the phase diagram. Let me illustrate on this graph here. So if you have only one component and one phase, let's say it's the solid phase, so we're at some region up here. Well, notice that I can change the temperature and the pressure as much as I want. Not drastically, but I can move around in temperature and I can move around in pressure independently, and I'm still going to be in the solid phase. Okay, so that corresponds to an area. However, if I had two phases in equilibrium, let's say the solid and the liquid, well, that means I'm along this curve, and in order to keep the same number of phases, I can only modify one variable at a time. Right? I can either modify the temperature and then the pressure automatically needs to change in order to preserve the equilibrium, or I could think about modifying the pressure, but then the temperature needs to automatically change. So I really only have 1 degree of freedom when I've got two phases in equilibrium. Likewise, if you've got 3 phases in equilibrium, you have no degrees of freedom. Any change in temperature or change in pressure is going to disrupt the equilibrium of the system. And so that's what's listed in these 3 points here. For a single component system, it is not possible to have more than 3 components, to have 3 phases in equilibrium. And that is because you would have too many constraints in the system for the number of variables. So for a pure system, we have only 2 variables, temperature and pressure. And if you had 4 phases in equilibrium, you would have this equation, that equation, this equation. You would have more equations than variables, right? So you can't have more constraints on the equilibrium than you do variables. And so the Gibbs phase rule for a single component system is that the number of degrees of freedom you have is equal to 3 minus the number of phases you have in equilibrium. You can generalize this. So here's a diagram corresponding to that. I guess I should have looked over here. Here in the alpha phase, we've got 1 phase and 2 degrees of freedom. Here along this curve, we've got 2 phases in equilibrium and only 1 degree of freedom. And right at that point, we've got 3 phases in equilibrium and no degrees of freedom. This type of point where you have 4 phases coming together is not physical. So this is an impossibility. You'll never see a phase diagram like this for a pure component system. You can generalize this to a multi-component system. The mathematics of this problem are explained in the textbook. I don't really need to run through them here. Here is the generalized Gibbs phase rule, where you've got C is the number of components in your system, P is the number of phases in equilibrium, and then you've got this plus 2. This allows you to calculate the number of independent degrees of freedom. That is going to include things like temperature, pressure, and then concentrations. Right, so concentration is now a variable that you can tweak when you've got a multi-component system. Well, the last parts of this discussion are really just walking through 3, interesting phase diagrams. So we'll start with carbon dioxide, and then we'll look at water and helium. Just a few notes here on this side, some peculiarities about these substances. So obviously carbon dioxide is a nonpolar substance, so there's very weak intermolecular bonding in the condensed phases. You may recall that solid carbon dioxide is called dry ice, and that's because the triple point of carbon dioxide exceeds 1 atmosphere. We'll see the effect of that in the phase diagram. For water, well, let's just do carbon dioxide first. So here is a phase diagram for carbon dioxide. Notice it's not to scale in the sense that there's a break along the pressure axis. So we have moderate pressures, and then all of a sudden, oh, we're going to shoot up to large pressures. Plotting that as a function of temperature, and we're looking at these different ranges. Here's the effect of the triple point pressure being so high. Here's 1 atmosphere. If you've got solid carbon dioxide and then you start letting it warm up at 1 atmosphere, you're going to encounter the solid vapor coexistence curve. You won't observe any liquid CO2. You're just going to go straight into the vapor phase. So you're going to undergo sublimation at 1 atmosphere. In order to see liquid CO2, you need to elevate the pressure above the triple point, and then as you increase the temperature, you'll cross into the liquid range, and then eventually you'll end up boiling the liquid CO2. Oh, we're just supposed to describe what happens when you go around this path here. So here we're starting, in the middle of the vapor diagram. We are dropping the temperature and increasing the pressure. That takes us into the solid. We increase the pressure and the temperature. That takes us to the liquid phase. And then if we drop the pressure back down, eventually we will end up boiling that liquid. Water. Oh, let me talk about the variation of the fusion temperature and the vaporization temperature with pressure. So here you have to, let's look at the vaporization curve here. So this is the vaporization curve. And so this corresponds to the boiling point as a function of pressure. So you can think of this as the independent variable and the temperature as the dependent variable. So as you increase the pressure on the substance, you'll see that the boiling temperature increases. The same thing is true for the melting point in this case. Right? As you increase the pressure, track this line here, the melting point also increases. That's not true for every substance. Most substances are like that, but it's not true for every substance. For example, it's not true for water. The melting point decreases for water as pressure increases. And this has to do with the fact that the molar volume of liquid water is larger than that for the solid, right? The liquid actually has, the molar, let me think now. The molar volume for the solid is larger than it is for the liquid. And that has to do with the structure of ice and hydrogen bonding. We'll also see some of the other polymorphs of ice that occur at high pressure. So here's a phase diagram for water. Okay, so we're plotting pressure. Notice it's a logarithmic scale. So we live down here. We live here at 10 to the 5th pascals. Okay, so this is our range here. And then the pressure gets very big as you go up. And so we are used to ice 1, right, and liquid water and then steam. But if you go to very high pressures, what you'll find is that the ice will undergo phase transitions to other phases of ice. That is, the crystal structure of the solid will be different than it is for our normal ice. And if you zoom into the triple point, what you'll see is that the melting point curve goes the other direction. It leans to the left, whereas for CO2 it leaned to the right. And so this corresponds to, as you increase the pressure, the melting point of ice 1 decreases. And that has to do with the structure of ice. So here is a little section of water. Here's the oxygens and the hydrogens. And they form this network of hydrogen bonds, and it has a very open structure. Okay, and so this makes the molar volume of ice fairly high. When you heat up the ice, what can happen is that the water molecules can then, as they start moving around and the crystal gets disrupted a little bit, you're going to get water molecules jumping into this pocket. and that's going to cause the density of the liquid water to be higher than that of the ice. So just following around the curve here, at point A, we are at ice 5. And then we increase the pressure, and we have a couple of solid-solid phase transitions. We'll go through ice 6 and then into ice 8. Then as we hold the pressure steady and increase the temperature, we go into ice 7. And then as we drop the pressure, we'll go back through ice 6 and then into the liquid phase. Now, a really weird substance is helium, especially at low temperatures. Helium atoms have extremely weak interactions between them. Helium-3 and 4, they behave very unusually at low temperatures. They have a normal liquid phase, and then they also have what's called a superfluid liquid phase, where if the temperature is low enough, helium-4, for example, is able to flow without any viscosity. That is, there's no resistance to the flow. And so you can see, if you look on YouTube, if you do YouTube superfluid helium, they'll show you videos where you can watch superfluid helium crawl out of a container. It'll crawl up the walls of its container and then fall down below the container. So there's all sorts of weird properties for superfluid helium. Helium-3 is kind of weird in the sense that it's melting. Its fusion, the enthalpy of fusion is it's exothermic, so that's odd. I don't know that much about that, but that was interesting to read in the textbook. Here is a phase diagram for this would be for helium-4. At very high pressures, you can have a solid phase. Okay, so this is very cold. Look at the temperatures. These are very cold, like 1 Kelvin, 2 Kelvin. Okay, so here's solid helium way up here. Here we've got the gaseous phase. And then over here we've got the normal liquid. So this is just an ordinary liquid. It's very cold. But what's weird is when you go to even colder temperatures, what you encounter is this so-called superfluid state. Okay, so it's still a liquid, but it's not like an ordinary liquid. It has all sorts of unusual properties associated with the quantum mechanical nature of matter, and it's quite interesting. This is called the lambda line. Supposedly, the shape of the line intersecting looks like a lambda. I guess I think it looks like that if I turn my head, but in any case, this is called the lambda line. So that's just some examples of phase diagrams. Here's another a crossover between the two liquid states of helium. So here you've got the ordinary liquid, and then this is this looks more like a lambda line to me. And then over here we've got the superfluid helium, and there's it looks like there's a jump in the heat capacity. Okay, and so that's indicative of a phase transition, right? Well, I'm going to go ahead and stop this video here, and we'll pick up with the other part of phase equilibria in the next video.